Okay, hello everyone. Yeah, I hope the sound is fine. So I'm Dimos. I'm working in a blockchain company called R3 in London. And this is one of the reasons I recently had to reread that paper and remember how cool it is. I want first of all to thank Renzo and USwitch for hosting me for a second time. And before starting, I want to explain what's the reason I like this paper a lot, or I love it. The main reason is that it helped people become aware of cryptography in a wider context, and it also helped establish blockchain as a primitive, as a concept, that led to a lot of other discoveries later on in related projects. So it helped a lot to disrupt the tech industry. So what was the problem that the paper is trying to solve? The main problem was that the fact that our financial system is based on trust. We have several financial institutions that are responsible for performing several tasks, and this has some drawbacks. For instance, these institutions are sometimes single point of failures. As you can see, for example, during the history in the crisis of 2008 in the US. Also, in some cases, there are many of those institutions that have to interoperate when we do transactions between multiple banks, for example. And because of that, data are duplicated between the different institutions, and they have to perform some reconciliation, which makes transactions much slower, and thus make business more difficult and less efficient. And the last one is the fact that because of that need for reconciliation and manual, perhaps, fixing of errors that were committed, this requires sometimes even more trust. And for example, you can see a contrived example of that in e-commerce websites. For example, in Amazon, when you go to do a purchase, you might have to go through several checks. Or sometimes when you make an account for a credit card, for example. So the main concept of the paper was what if we could transact with each other without the need of a third party directly? And what would that mean? What would the difficulties be with that, and where it would help, perhaps? So it all started 10 years ago. By Satoshi Nakamoto, who is a nickname, and nobody knows who he is or she is. And it all started with his email where he was trying to explain what he tried to build, and he gave a link to the paper. And there are, so the main concepts of the paper are, first of all, a system of electronic cash, where, as we said, there is no third party that is trusted by everyone. The network is fully peer-to-peer, which means the various nodes of the system communicate with each other directly by broadcasting. Messages do not go through a central point in the network. Participants can be anonymous. This is based on a concept of public and private keys that we will see later on. And then there is also a proof of work mechanism, which is used for different things in the protocol. We will see later on in detail what these are, but mainly the first one is this is the way, since we don't have a central third party that mints new coins. This is one way to provide the participants in the network with the ability to mint new coins. The second one is, again, because of the reason we don't have these third parties that make sure that something is not spent twice, this goes on to the participants, and this mechanism ensures that nothing is not spent twice. So this paper, most of the ideas that this paper poses are not completely new. They pre-existed, but the elegance of it is that it takes all the concepts and puts them in a single protocol in a very powerful way. The main two concepts are hash functions and digital signatures. So before going in the paper, we will just do a very quick introduction in case we're not fully familiar with them. So the first concept is hash functions. A hash function is a function that can map some data of arbitrary size to data of a specific size. So for example, here we map a string of arbitrary size to an integer of 2 digits, for example. And it can be used for a very, very common use case is for building dictionary data structures that have very efficient operations. But they're widely used in cryptography as well. And in that case, we mostly speak about cryptographic hash functions, which have some more requirements. So hash functions have a set of properties. The most useful of them are the ones we saw here. First of all, they have to be deterministic. Every time we execute the function with the same input, it has to give the same output. The second one is they have to be easy to compute. And as we'll see later on, this means that when we have, when someone has computed a hash function for something, and another one gets the same hash, he should be able to verify whether that hash corresponds to that data very easily, very quickly. We will see where that is useful. The third property is that hash functions are non-invertible. So having just a hash, it should be computationally hard to find out what is the preimage. That's how it's called. So what is the data this hash originates from? And this helps in avoiding tampering of data. So if someone has some data in their hash, it should be difficult for him to create some other data with the same hash and trick the system. We'll see later on how this is done. And the second preimage resistance is what I mentioned just now. It's slightly a variation of the first preimage, which is if you have the data and their associated hash, it should be, again, computationally hard to find another piece of data that maps exactly to the same hash. So digital signatures is a way to sign a piece of data and provide the proof to other people that this data was signed by you. And the way it works is it's again based on mathematics, but I won't go into full detail here. So the way it works mechanically is that we have, for example, Alice and Bob, and Alice wants to sign some piece of data. So what she does is she creates two keys, a private key and a public key. These are they could be just integers, for example. They're a piece of data. She holds the private key private, secret. She only knows about it. And she distributes the public key to everyone she wants to exchange data with. After she's done that, she can get a piece of data like, hello, Bob. Sign it. So using a function that gets as an input that piece of data and the private key, it generates the signature, which is what we see on the bottom right. And then, so this is generated, you can think of it as the hash using a hash function, very simplistically. And then she shares both with someone else she wants to. And then that someone else, like Bob, is capable with the same mechanics, using the public key that Alice shared with him, and running it through the message, hello, Bob, and ensuring that this gives the same signature. Right? So he's sure that Alice signed that piece of data, because only Alice has the private key to sign it. Starting now with what this paper proposed is, as we said again, it's a way to have electronic cash. So it is based on the notion of coins, but it has a slight difference with the notion of coins we have in the physical world in the following sense. In the physical world, coins can exist independently of transactions. So I can have a coin here in my desk, and then later on I might transact it with someone else for something else. But in Bitcoin, coins do not exist independently. They coexist with transactions. So a coin is always an output of a transaction. This is what the data model is. So a transaction is a transaction between two parties, and it has a set of inputs and a set of outputs, right? Inputs are the coins that go into the transaction, and outputs are the coins that are the output of the transactions, are given to someone. Right? In that example, for instance, we have the transaction 103, and that transaction gets as input 2 coins from Alice, 1 coin of value 10 and 1 coin of value 2, and it transfers them to Bob as a single coin of value 12. Based on the fact that coins are always part of the transactions, these coins that were the input of transaction 103 must have been the output of historical transactions in the past, right? And of course, there is also, as you see, this forms a graph of transactions, and there will be always some transactions in the end of the graph that have coins that only have been present as outputs and not as inputs. And these are called in Bitcoin as UTXO, which means unspent transaction outputs. And it's essentially the data, the money that are in circulation in the economy. There is also the capacity for splits here. So if, for example, Alice would need to give a value of 11 to Bob, she could give those 2 coins, and the output could be 1 coin of value 11 and then 1 coin of value 1, which goes back to Alice. So that's another difference to the physical world, in the sense that you can split all kinds of coins into whatever fraction you want, which is quite handy. So as I said previously, this forms a graph. So every time you want to transfer some money to someone else, you must have his public key. That public key acts as his address. It acts like his bank account, for example, right? So what you do is you get the public key of that person, and then you get the ID of the transaction that you want to spend coins from. This is what is shown as hash here. Then you generate a hash out of those 2 to compact the data a little bit, and then you sign them with your private key. Essentially, by that process, you sign that you are giving that money to whoever has that public key, right? And that goes on and on. But this, I can acknowledge that it's quite complex, and of course it creates a lot of questions. For example, one question is, where do all the coins come from, right? If they're part of every transaction, they should have been born it's a catch-22. So another question is, but then how can we prevent people from double spending, right? I could sign the same transaction twice and give it to different people. So let's tackle them separately. First of all, how are coins born? So in the beginning, in the birth of Bitcoin, there was this event which was called the Genesis. What happened during this event is that there was a single transaction, which was the first transaction, and that transaction was the only one that had no inputs and only outputs. The rest of the transactions after Genesis have to preserve value, right? They should not create value or make value disappear. So this is the first transaction that introduced some coins to the economy, and is usually in Bitcoin and other systems that follow the same blockchain structure. This is hard-coded in the system, so that only these transactions are allowed to have this kind of character. Of course, if we say this block created only 100 coins, This wouldn't be very practical because as the coin is adopted, we want more coins, right? So there was another mechanism to introduce inflation and mint some coins, as we said. So as part of every transaction, so when nodes verify transactions, they also get, so there is a small amount of coins created as part of that validation, and it goes as a reward to the node. So more coins are generated as we go. So the second question we saw previously is how do we prevent double spending? So the way it is done in the physical world is we have our bank, which is responsible for validating all the transactions, and it keeps a history of all the transactions and performs that task. Also in the physical world, sometimes, if you, that's another interesting concept. If you have a coin, you cannot double spend it, right? Give it to some cafeteria to get a coffee, and then you cannot give the same coin to another cafeteria unless you go and steal it. So the physical presence of the coin prevents double spending by itself. In the digital world, that is not the same. So what you need to do is you need to have the concept of a server, which is a timestamp server, that is responsible of observing everything and keeping a memory of what has been spent and what hasn't been spent. And this is trivial to do if you have a third party, a central point where everything is sent there and validates everything. But if you have a pool of nodes that they're all equal, and they all do the same work, it's much more difficult to do. So this is the gap that the proof of work mechanism captured. And so what that did is that the proof of work consists of must be really hard to produce, to solve, but it must be very, very easy to verify, right? So every node that needs to validate a transaction has to work hard to be able to validate the transaction, but then all the other nodes can very quickly ensure that whatever that node did is legitimate and the transaction is valid. We will see later on, it seems counterintuitive, but we will see how it works. It introduces some dynamics. So for example, that riddle could be the following. You have a transaction with a hash, and you also you have to find a piece of data that when hashed with that transaction, it gives a number with a specific number of trailing zeros. This piece of data you have to calculate is usually called nonce. And this is one of the problems that mathematically is hard to compute, and there is no efficient algorithm to do so. So you have to brute force it. You have to create a nonce of, assign 0 to nonce, and then increment it by 1 until you find the number. So it's very difficult to do so and slow. So this mechanism has some properties that are quite useful. The first one is that all the nodes, based on that, all the nodes have a voting power to whether a transaction is valid. And that voting power is related to how much computing power they have, right? Because the more computing power they have, the more of these riddles they have, they can solve quickly, and then the more transactions they can validate. The second one is, as I said previously, as nodes validate transactions, they get some reward back, right? And that reward is creating the inflation in the economy, is generating new coins. So as you go, theoretically, you would want probably to reduce that generation as you go and as the economy grows to limit the inflation. And for this reason, this mechanism has this nice property that you can easily tweak that riddle as you go and adjust its difficulty. So as the riddle becomes more difficult, perhaps it can create different amount of coins. So as you go, you adjust the difficulty, and then you adjust in the same way how many coins are generated and what is the inflation of the coin. In practice, as we saw with the price of Bitcoin, it doesn't hold practically always because it's subject to other variables, but theoretically it should work. So, and we will see later some computations about this. One small addition to that, so I tried to simplify it a little bit in the beginning, but because of the fact that this computation is hard, what nodes are doing is they're gathering transactions and validating them all together in a single block. So essentially all the connections we saw previously between transactions, they are between blocks of transactions. And that's why it's called blockchain. Okay, what's the protocol? Just to go through quickly, that should be quite straightforward. So the way it happens is we have a pool of nodes that participate in the economy, and then nodes act as clients as well. So I want to perform a transaction with someone else, and I can also be running a node. So I create a new transaction on my node. That node broadcasts that transaction to other nodes as well. Then these other nodes collect transactions for multiple people and then gather them in a block, and then start working on the proof of work for that block. Try to find that nonce that creates that number with the trailing zeros we saw. When they do that, they form that block, they form the result of the proof of work, and they broadcast to other nodes. Then the other nodes check first of all that the proof of work was valid, that the other node has calculated, and they also check their history of other transactions, whether that same coin has already been spent. So this is done by all the nodes, this double spending check. And then what happens in the end is essentially when nodes receive blocks and verify them, they also approve them by working on top of that block. So as blocks calculate new blocks, validate new blocks, they put them on the existing chain and make it grow. Right? And if you think about it, there is a possibility that this chain can diverge. So we can have multiple chains because all these nodes work in parallel. There is no central node. And what that means is that if you have multiple chains, what the protocol imposed is if there are multiple chains, the longer dominates. So if I have a chain that consists of 5 blocks, so I received one block, right? I receive one block from one node, and then I start working on that. And then I receive 2 blocks from another node. I stop working on the first chain, and then I start working on the second one, right? Because it seems to be more accurate. Of course, this sounds dangerous, right? And this is where double spending gets in the picture. So how you could trick that system into doing a double spending, right? So we have these 3 nodes, and then in the middle we have other nodes of the system that validate transactions. And the guy on the left is the guy that wants to do a double spending. So what he does is he creates a new transaction, he broadcasts it to the network. That transaction is supposed to be giving some coins to PKA on the top right. At the same time, after he does that, he creates a second transaction to PKB, exactly with the same coin, and he tries to work on his own in the proof of work for that block, secretly, without anyone knowing. After a while, the nodes in the network collect that transaction in their blocks and do the proof of work on their own. And then eventually, they broadcast this block with the transaction. PKA gets that, and then he knows that he's been given these coins. And at this point, he's sending a product, perhaps, to PKZ. So after PKZ receives that product, he tries to finish that work he did, the proof of work for the second transaction, and then he broadcasts this new block in the network. Right? And in the meanwhile, with all that work he did, he has managed to create a longer chain than what the rest of the network has created, which is a bit difficult. Yes, that's true. So after the nodes get that second chain, because the chain is longer than the one they've created, they self the previous one and they start working on the new one. So they create new transactions, they add them to blocks, and they broadcast the new chain. So eventually, this new chain is broadcasted to both people, right? To both nodes. And then at that point, what this means is that PKA doesn't own the money anymore. If he tries to spend that money, he won't be able because the transaction validation will fail. And PKB owns that money, right? However, PKA gave the product to PKZ. And so in order to do double spending, because the system reconciles itself, in order to do a double spending, you must have what is called as a side channel. So you must be transferring a value not only in bitcoins, but also in other material, the product in this case, because the product cannot be reconciled. It's outside the Bitcoin system, right? So how is this prevented, if it's possible, then, in the Bitcoin network? So the way this is prevented is because, as we saw previously, while the malicious node tries to trick the system, he's working on the proof of work, but all the rest of the nodes in the system are doing the same thing, and it's the whole network against him. So in order for him to outperform everyone and create a longer chain, he has to control 51% of the power of the network, right? This is why it's called 51% attack, which is hard if we consider that this was supposed to be used globally, so the network is theoretically expected to be very big, and no one should be able to have that much computing power. There are also some other variables that make that harder, which is, for example, that if someone had, let's assume that someone has all this power, computing power, then it would be more efficient for him, instead of trying to trick the system, to validate legitimate transactions, because he would get a lot of rewards, and that would give him more money, probably. And the last one is that by tricking the system, this node undermines the health of the system, because if double spending is possible in Bitcoin, then people trust less Bitcoin, and the value of Bitcoin will go down, right? So all the Bitcoin he gathered, and we assume he has a lot because he has a lot of computing power, are worth less. And this is called the proof of stake. It's slightly different to the proof of work concept. It's called proof of stake because the more stake you have in the system, succeed, right? So the less you want it to be vulnerable. And in the end of the paper, there are some calculations which include a lot of mathematics, and I won't hide it. Mathematics is not my strong point, so I won't try to explain that stuff. Essentially, what Satoshi is trying to do is he's drawing an analogy between this problem and a process called binomial random walk, which is if you have two people competing, and each one has some possibility to make a step forward or back, and then you have a way to compute what's the possibility for one of them to win the game. It's very similar to the Bitcoin problem we're seeing, because in that sense, nodes are competing for validating the next block, putting the next block in the chain. And at every point in time, there is a point where either the malicious node gets a step ahead, or the rest of the network gets a step ahead. So he models that in these two variables. P is the probability that the honest node finds the next block, and Q is the probability that the attacker finds the next node, the next block. Sorry, that's a typo. And then he tries to calculate the probability, which is spelled as QZ, which is the probability that the attacker will ever catch up from Z blocks behind. We will see how that is used. So we will see that this probability drops exponentially as we increase Z. And for example, in the end, he calculates, so he says, okay, if we want to make sure that this probability is less than 0.1%, which is quite low, so there is less than 0.1% probability that the attacker will be able to perform this attack, then what are the number of blocks we need to have this transaction be deep in to achieve that possibility? And he showed that between we see these two numbers 5 and 8, we can achieve that. So in the current implementation, if I'm not wrong, a node waits until a transaction is 6 blocks deep in the blockchain until he's sure that this won't be able to be spent twice. So the paper also covers some other enhancements. One of them is deterministic wallets. What that is there is a way to deterministically generate additional keys based on a single key or a single random seed. And this helps because if you can achieve that, then every time someone makes a transaction, he can create a new public key. So all your transactions have new public keys, and then no one can track who is getting all that money. So there is increased privacy, but at the same time, you don't have to store all the different public keys. You only store that single key, the one public key you need, and then if you want to recalculate the other keys, you can do that through this deterministic algorithm. Yeah, I forgot to make that appear, sorry. So the second one is some space savings via Merkle trees. So Merkle trees are a data structure where you can form, so if you have a piece of data that is composed of multiple parts, you can form a tree structure and then hash pairs of these pieces of data recursively until you end up with a single element, which is the root of the tree. That can be used in a lot of different ways. For example, in some systems like DynamoDB, it's used when people want to compare whether they have exactly the same data. Instead of exchanging the whole data set, they exchange only parts of the tree. And they are able to do that by exchanging much smaller amounts of data. But here, the way it's used is, the one way it's used is by doing garbage collection and not having to store all the data. So if all these blocks you have are of this form, then after a point, you will have some transactions that have been, some outputs, some coins that have been already consumed a long time ago. And they won't be needed in order to validate new transactions, right? Because for the validation, you only need whatever is not consumed. So eventually, you can separate these parts from the Merkle tree and garbage collect them, remove them. And in this way, you have the root hash, the root node of the Merkle tree, which you use when you walk back the chain. To make sure that every transaction has the right hash of the previous transaction. And at the same time, you keep only the transactions that have unspent output. And also verifying that these transactions are legitimately part of this block based on the hash properties. The second saving we can achieve with Merkle trees is what is called lightweight transaction verification, which means that you have, so as we said, you have all these nodes in the network, and they all validate transactions. But then, without that, every node would have to broadcast everything to everyone, and that would be a lot of data exchanged between nodes. But then with this approach, you can only exchange whatever is relevant to you. So I can only send to another node only the transactions he will need for validation. It's a similar concept to the first point. And using that data, this node can first verify that the blockchain is valid by checking the hashes of the different blocks and making sure that every block is being created legitimately based on the previous one. And also make sure that the transactions he sees are valid and are not like fake transactions, because their hashes recursively form part of the Merkle tree. So these were the ideas presented by the paper, and in an effort to see what happened after 10 years, which is interesting in my opinion, we can see some data and see how the design decisions, what are the effects they had. So we mentioned, for example, that the 51% attacks are only possible if someone has that much power. And looking at the statistics, at recent statistics, for example, we can see that some of the pools, of the validation pools, are quite big. For example, one pool has almost 30% of the computing power, of the hashing power, and also 81% of the power is located in China. And this increases the risk of 51% attacks, but it also has another side effect, which is the following. It's not reflected so much in the paper, but it's practical. So every time there are improvements to the protocol, because Bitcoin is evolving, every time there are improvements in the protocol, nodes have to essentially have to approve the new things and accept them and run them in the node. So run the updated version of the software. And they're not forced to do so. It's optional for them. So the more power someone has, the more control he has, whatever is introduced in the protocol, right? It's not very democratic, we would say. The other one is, as we said, things that one of the problems this paper was born out of, it was that transactions were not very efficient in the financial world. So this depicts, compares the global power consumption from Bitcoin with the power consumptions from everything else in several countries in the world. And where you see green, that means that the global power consumption from Bitcoin is more than or very close to the power consumption of that country. So perhaps it's not that efficient. It's not that more efficient than the current financial system. And the last thing is transaction finality. What that is that, so whether something has been double spent in the computer science research is called as the consensus problem. So multiple nodes in a system have to agree on a specific value. In our case, that value is whether something has been spent or not. And there are several algorithms for that and different failure models. And one of them is called Byzantine failures, which means that nodes can fail in very unpredictable ways and do weird things. So they can be compromised by a malicious actor, and that actor controls the node. Or we might have weird programming errors that make the node misbehave. And this is, in general, a very difficult problem to solve consensus for systems with Byzantine failures. And it's usually taken out of consideration because companies control the nodes usually, their servers. So the Bitcoin solved that problem because nodes are not controlled anymore. And it solved the consensus problem with Byzantine failures, which is quite powerful. But then there is a slight difference. This is the concept of finality. So finality is where the value is agreed. And finality can be either deterministic or probabilistic. So deterministic finality means that when the nodes have agreed, when the system has agreed on that value, this can never be reality, meaning that this might need to be taken back, and it's wrong, even if this possibility is very, very small, as we saw in Bitcoin. So Bitcoin implements probabilistic finality, right? And as we said, nodes wait for a block to get deep in the blockchain, around 6 blocks, before they can be sure that this transaction is valid and they will get their money and it won't be double spent or reversed. And every block is verified around every 10 minutes. So if they have to wait for 6 blocks, they have to wait for around an hour. And here we can see that this also fluctuates a lot. So it can get from 1 hour to up to 4 hours, for example, or 3 hours. And this also ties back to the point that, as we saw, one of the problems initially was that transactions are slow, and Bitcoin would come to improve that. But I'm not sure whether financial transactions can get up to 4 hours, for example, right? They're much faster in most of the contexts. So that's also one more idea that can be challenged. So all that said, in order to conclude, I think this paper has produced a lot of new ideas. And first of all, as we saw, it has given a nice novel algorithm for solving BFT consensus problems, even if it's with non-deterministic finality. Second one, as we saw, is the fact that it established blockchain as a building block, and then we can see there were a lot of systems that leveraged this idea with with much more interesting applications. And the last one is it helped people review and reconsider the trust model we have for our financial systems, and perhaps improve a lot of stuff, since a lot of companies are adopting ideas from the paper in real life. So that's all, I think. I have made the slides available. I guess Renzo will also share them with you. Thank you. Are there any questions, by the way? Yeah.
Yeah, I never understood really this coin, the concept of a coin. I always thought of Bitcoin from a double entry accounting point of view, that you have accounts and you have transactions, and the balance of a given account is given how much previous transactions have been transferred to that account. And I was always thinking that double spending is that, so if, for example, if I have 2 coins on my account balance, then I can spend one, give it to A account, and another one to B account. But this coin concept seems to me that it conflates. So is the system checking my balance? So in one block, I'm not spending more than the amount of balance I have, or is there a coin? Is there really a coin concept? So if I spend, my balance is 2 coins, but if I spend 1 coin here and 1 coin there, it might be the same coin.
Yeah. Thanks for the question, by the way. I might have complicated a bit in some slides, and that's why it might not have been clear. So every coin...
Can you repeat the question?
Yes, sure. So the question is, in triple entry accounting, it's usually very easy to verify whether we have double spending, while in this system where you have these 2 concepts of transactions and coins, it's not very clear whether double spending is actually prevented. So what I didn't make very clear perhaps is that the way coins are modeled is every coin is composed of the transaction it's the output from, so the ID of that transaction, and an index that is showing which output of the transaction it was, right? So that's why I said the coin does not exist on its own. It's always the output of a transaction, right? And so what the validation does is every time you are going and validating a transaction, you can verify whether that transaction has been spent already, right? The output of that transaction. The way you do that is you've been through all the history, so you are keeping a memory of what has been spent, right? What has been spent is the transaction IDs, right? And their associated outputs. So this is the way you can verify whether a coin has been spent or a transaction has been spent. Let's say transaction output has been spent. The problem is that in triple entry accounting, the example you mentioned, for example, you have a single Excel spreadsheet where you keep track of everything, while in Bitcoin, everyone has its own Excel spreadsheet, right? And this is where it gets a bit messy. I hope it clarified it a bit.
You reconcile those separate Excel spreadsheets to find out what the value of your coin is currently, the amount that you have. You have to have the whole history.
Also, I had the same problem at some point to think about this and to understand the concept. And I think the problem is that there's not really a concept of accounts. It's just the coins in the system. So you don't say your account has 2 coins. There's 100 coins, and you either can spend one or not because you have the private key for the last transaction. So the system is not calculating and reconciling your account. It's just verifying that that coin is the result of a single chain of transactions up to the beginning. So that's the thing, because usually we think about accounts, like I have this much money in my account, whereas in the Bitcoin system it's not. There are no accounts. There's only coins, and either you can spend it or not. You have control over it at this point.
That's very true. So what happens is that you only have coins and transactions, and the way, if you have a wallet, for example, or a node, it never, so we have the concept of accounts. It's, as we said, the public keys, right? So by the public key, you can identify what someone owns. But if you see, for example, a Bitcoin wallet or a node, they don't have the concept of a bank account on its own, holding the balance of it, but they calculate it as a materialized view. So what they do is they go through the whole graph, identify all the transactions that are giving output to this public key, and that have not been spent already. They sum them up, and this is the balance. So the balance doesn't exist as a separate number. It's materialized, it's calculated at runtime.
So is every coin a blockchain, or is there one single blockchain in any given network?
Sorry, can you repeat?
Is each coin, like I'm trying to actually understand what the blockchain is. Is each coin a blockchain, or is there one single blockchain?
So each coin is part of a transaction, right? It's the output of a transaction, right? A lot of transactions form a block, right? And blocks, and there is a linked list of blocks, and this is the blockchain. So the blockchain essentially contains all the coins.
And how do you decide which transactions go into a block? Because it sounded like you said like all new transactions get collected into a block or something.
Yep.
But I mean, what's the boundary around that? What are all
so a block goes into the blockchain as long as the proof of work is fine. So someone calculated the proof of work and is valid, and the nodes validate that this block, all the transactions in this block, are legitimate in the sense that they don't double spend anything.
How often?
Otherwise, it's rejected outside the blockchain.
New block created 20 or 30 minutes?
10 minutes.
Every 10 minutes.
That's adjustable depending on how the difficulty of the algorithm changes, and a lot of other things.
Time window, which block you're going to have your transaction in.
Oh, so every 10 minutes it says, okay, what are all the transactions that happened in the last 10 minutes, and that becomes the next block. So does that mean that it takes about 10 minutes, or as up to 10 minutes?
It doesn't block at that point, so it doesn't say, okay, I'm not doing anything for the next 10 minutes. Okay, I'm working now. During those 10 minutes, it's trying to solve that problem.
Okay.
Theoretically, right?
But there's also an incentivization structure, right? So if I want to spend some of my Bitcoins, if I have some, I've got to convince a node to make a transaction for me. and then solve that.
Yeah.
transaction.
So yeah.
If I don't convince the node to put it in, then he doesn't put it in.
Yeah, so that's another thing I missed. So the question is, there has to be some more incentive. So besides the coins that are minted on every validation, someone can also put some rewards for the miner. So the transaction will be whatever you give to someone plus some more. You give some incentive to someone to make that calculation and get the block in the blockchain. Propose it.
So you said when you I don't remember the terminology, but when you approve the blocks, you basically calculate the hash, find a hash of the previous block hash, transactions that you're going to confirm, and some nonce that you're trying to find to have like a certain amount of zeros. So like if I'm trying to win the race and find the hash first, would it not be in my in my interest to instead of trying to find a hash for all the pending transactions that I know of, instead of like trying to find a hash for all possible subsets of these transactions, so I'm kind of getting more possibilities at the same time if I can parallelize my search.
Yeah, that's possible, definitely. So the question is whether you have a specific set of transactions you have to calculate proof of work for, or you can be flexible. You can do whatever you like, as long as you satisfy. There are some things you have to satisfy. For example, how many transactions have to exist in a block. Okay. If it's 10 transactions, you can't put 8 transactions there. It has to be 10.
I didn't know there was a lower limit, for example.
But then which transactions, it doesn't matter. You can like be working parallel in many things and only broadcast the first you solve, things like that.
Okay.
So my question might be a bit unrelated, but I know that there are like a lot of Bitcoin clients. Which one is the prevalent and mostly used one, and why is it like mostly used? I know like there is one like Bitcoin client in C, and I think there is also like other languages.
Yeah, the question is, there are so many wallets, and which one is the best one? I think the right person to answer that. It requires more search. Because a lot of wallets have bugs, there have been a lot of hacks, so I wouldn't want to give an opinion on that. Honestly, I don't have so much data.
So there's a big, obviously, payments directive coming in UK and Europe, the ST2, which basically means all transactions over a certain amount have to be done by two-factor authentication. It might be taken a slightly off topic. If you have obviously big players in China that can basically say yay or nay on pivoting, how would you implement something like proving all transactions by two-factor if China doesn't want to implement it?
If China doesn't want to implement it?
Well, yeah, I mean, essentially, you've got a small demographic that can make decisions. All transactions in Europe have to be approved by two-factor. How would Bitcoin implement that?
Yeah, so the question is, we have like a new directive. I don't really know what that is about, but anyway. And so how can you make sure that the network can be adapted to that, right? Adopt a new feature or something.
And
so
it also moves on to like the anonymous bit.
So this is what I described previously. There is this concept of, this is called BIP, I think, Bitcoin Improvement Proposal.
Yeah.
So people that are part of the community create these proposals. They're like design documents of a new feature. And then these are being developed and then are given to nodes for them to adopt. Of course, because of the dynamic I said previously, it's optional for them to adopt. So at least 50% of them, 51% of them have to adopt them, right? And this is because if you're in the minority, you won't be able to cooperate with the rest of the network. So at that point, you will have to adopt it. That's the answer I would give. Yeah, it's a much more complex question, though.
Okay, so it's kind of.
If you dig deeper into these BIPs, you will probably be able to find out how they are adopted and what's the exact process that nodes go through to update their software.
Let's go to you.
Okay.
Stay.
Yeah. Thank you very much.
Thank you.
See you in the video.